Hello everyone. Welcome to the session on Python Pandas for data analysis. The first step in any Pandas-based program is importing the library. We use the statement import Pandas as PD. Here, Pandas is loaded into memory and the alias PD is created for convenience. This shorthand is a widely accepted industry convention and allows us to write cleaner and more readable code. Once Pandas is imported, we can start working with data structures such as series and data frames. pd._version_ gives the version of Python. Now let us understand the most fundamental Pandas structure, the series. A series represents a one-dimensional labeled array. In the code, we create a list of numerical values and assign custom index labels such as X, Y, and Z. When we use pd.series of data, index is equal to labels, Pandas maps each value to a meaningful label rather than relying on position alone. This label structure makes data interpretation clearer and reduces ambiguity during analysis. Next, we move to the core data structure in Pandas, the data frame. A data frame is a two-dimensional table similar to a spreadsheet or a database table. In the code, we first create two independent series, one representing product names and the other representing sales values. These series are then combined column-wise using pd.dataFrameOf. The result is a structured dataset where each row represents an observation and each column represents a variable. This tabular structure forms the backbone of most data analytics tasks. In real-world analytics, data usually comes from external files. To load such data, we use the pd.read_csv of function. This command reads the CSV file and converts it into a data frame stored in memory. At this point, the data is no longer raw text. It becomes a structured object that Pandas can analyze efficiently. Once the data is loaded, the first task is initial inspection. We use df.headof to view the first 5 rows of the dataset. This helps us understand column names, data formats, and whether the values look reasonable. Similarly, df.tailof displays the last 5 rows, allowing us to check for missing or incomplete records at the end. To get a technical overview, we use df.infof. This command provides details such as the number of rows, number of columns, data types, non-null counts, and memory usage. Finally, df.shape tells us the exact dimensions of the dataset in terms of rows and columns. After inspection, we move to data summarization. The df.describeOf function generates descriptive statistics for numerical columns. It reports measures such as mean, minimum, maximum, standard deviation, and quartiles. This statistical snapshot helps us understand data distribution and detect anomalies early in the analysis. For categorical variables, we use the value_count_of function. By applying this to a column like category, we can see how frequently each category appears. This is particularly useful for segmentation analysis and understanding data composition. To examine relationship between numerical variables, we use df.corref. This function produces a correlation matrix where values ranges from -1 to +1. A value close to +1 indicates a strong positive relationship. A value close to -1 indicates a strong negative relationship. And values near 0 suggest no linear relationship. Correlation analysis is essential in exploratory data analysis and predictive modeling. Often we do not need the entire data set at once. To select a single column, we use square bracket with the column name, such as df of outcome. This returns the column as a series, enabling focused analysis on a single variable. Finally, we look at filtering data. By applying a condition such as df of age greater than 50, we extract only those rows where sales exceed a specific threshold. This technique is widely used in business analytics to identify high-performing products, customers, or regions. Thank you for listening, and let us now move forward to hands-on practice using Jupyter Notebook.